I would like to welcome the audience. My name is Balázs Somodi. Me and my co-author Balázs Kövesdi are from Hungary. The title of this presentation is Flexural Buckling Resistance of Rectangular Welded Box Section Columns. First of all, I would like to introduce the topic and highlight the background and motivation. The research topic is important because the application field of high-strength steel is growing nowadays in the civil engineering practice. The production cost of high-strength steel material getting cheaper and cheaper compared to the normal strength steel. Therefore, the high-strength steel material could be more economical for more and more types of structure. In high-strength steel structures, due to high yield strength, smaller sections can be used. Therefore, the slenderness of the structural elements is usually smaller. So the stability failure modes are highly important. However, the application range of the current Eurocode is limited up to S460 material grade. To determine the column buckling and plate buckling resistance. In the international literature, the related research is usually dealing with I sections or square box sections. There are quite few results for rectangular box sections, but these type of sections are still frequently used in the engineering practice. Therefore, the highlight of this research is about the flexural buckling behavior of rectangular welded box sections made of steel grades from S235 to S960. The research is based on numerical simulations. Let me show some literature overview. In Eurocode, the flexural buckling resistance is calculated based on the buckling curves. Table 6.2 in Eurocode defines which curves should be used for which section types. This table does not differentiate square and rectangular cross-sections from each other, but there is a limit for the width over thickness ratio which decides whether B or C curve is the appropriate for welded sections. Because of the shorter side, a rectangular section satisfies one of these equations more frequently. So a rectangular section more likely requires the use of lower buckling curve than square section. In 2018, Somodi and Kövesdi published a modified buckling resistance calculation method where a new reduction factor should be used instead of the predefined buckling curves. According to this method, the reduction factor theoretically depends on the aspect ratio of rectangular cross-sections. So the purpose of this research is to figure out whether square and rectangular sections should be differentiated when calculating flexural buckling resistance or not. I would like to introduce the numerical research program carried out. A parametric program is made using deterministic numerical analysis. Two different analysis types were examined. One with realistic geometric imperfection plus residual stress, and one with the equivalent geometric imperfection defined by the Eurocode. 5 different variables are used: steel grade, plate thickness, cross-section class, aspect ratio, and global slenderness. 6 steel grades, 4 plate thickness, 3 cross-section classes, 5 aspect ratios, and 9 different global slenderness are examined. This means that all over almost 6,500 virtual experiments are calculated. The research aim was to examine the flexural buckling behavior of rectangular welded box sections and clarify the effect of aspect ratio and yield strength on the buckling resistance. Let me introduce shortly our numerical model. It is a fully shell model. GMNI analysis is carried out using displacement control loading and pinned end constraints around the weak axis of the cross-section. Therefore, buckling failure occurred around the weak axis for all the specimens. After the virtual experiments, the maximum force and the axial displacement belonging to the failure are determined and recorded. In order to set up the parametric calculation program and get accurate enough results, it was needed to predict the axial displacement at failure for all the 6,500 cases. To do this, axial displacement at failure is analyzed and correlations are found. The axial displacement at failure depends on slenderness, aspect ratio, thickness, and cross-section class. These dependency functions are determined and used to predict the axial displacement at failure for all the 6,500 virtual experiments. Finally, I would like to show the results regarding the flexural buckling resistance. First, the case with realistic imperfection plus residual stress is examined. The key reduction factor is calculated for all the virtual experiments, and those are compared with the buckling curves of the Eurocode. It is found that the results mainly are between curves C and A, and the yield strength influences the best which curve is the appropriate. In the following steps, the effect of aspect ratio is examined. To do this, a k-rect factor is calculated, which compares the reduction factor of a rectangular section to the corresponding square section, as you can see in the equation. The obtained k-rect factors are analyzed and correlations are found. In these graphs, on the vertical axis, you can see the calculated k-rect factors. On the horizontal axis, the non-dimensional global slenderness is presented. The results show that the increasing of the aspect ratio decreases the resistance, but this effect is highly dependent on the global slenderness. There are global slenderness ranges where this effect is negligible, but in other slenderness ranges, the effect of the aspect ratio could reduce the resistance even up to 8%. If we analyze the curves, we can see that in the lowest slenderness range, when fully plastic failure occurs, the effect of the aspect ratio on the resistance is almost zero. Also, in the high slenderness range, when fully elastic failure occurs, the effect of the aspect ratio on the resistance is lower. However, in the middle slenderness range, which means non-dimensional slenderness is close to 1, the effect of the aspect ratio could be quite big. Next to the slenderness, it is examined how plate thickness, yield strength, and cross-section class affects the resistance decreasing effect of aspect ratio. It is found that these parameters also influence this effect, but influence only slightly. In the next step, the same numerical program is executed, but applying the equivalent geometric imperfection without residual stress. It is found that the buckling resistance still depends on the aspect ratio, but the way how the aspect ratio influences the resistance is different without residual stress than applying residual stress in the model. This shows that the applied residual stress model has a serious impact how the aspect ratio affects the flexural buckling resistance of rectangular section columns. As a conclusion, I would like to summarize our results. It is found that the rectangularity, so the increasing of the aspect ratio, could reduce the normalized column buckling resistance by up to 8%, which is currently not considered by standards. It is shown that this resistance decreasing effect of the rectangularity strongly depends on global slenderness and also depends on the applied residual stress model. And therefore, to further analyze this topic, accurate knowledge of the residual stress pattern on rectangular sections is essential. However, there are only a few residual stress pattern research for rectangular sections in the literature. Therefore, this needs further experimental research to have an appropriate knowledge of the residual stress pattern on rectangular sections. Thank you for the attention, and also I would like to thank the financial support of the new National Excellence Program of the Hungarian government.